So as I was saying, I'm one of the few experimentalists that are in the crowd today, but I have used theory or computations in order to further my program. And today I just want to stress the importance of this symbiotic relationship between experiment and theory. And I'll just show a couple of examples, somewhat recent, recent examples of how we've used theory to complement our experiments and vice versa. And mainly, yeah, is there a way that we can dim the lights a little bit? Better? Okay. So what I want to stress today is that, in general, we are trying to look at material properties at all scales, not just length scales, but also time scales, especially since our experiments here are done on, micron-sized samples, and we're looking at crystal structures, and among other things, and so forth. But then we're trying to then go ahead and look and take these properties and then apply them to the Earth. Okay, so we've got very large length scales. Time scales as well. Our experiments are on our own time scales. They might be seconds, minutes, hours, and so forth. Yeah, let's see. So in terms of trying to couple both the theory and the experiment, what I came up with 4 different ways that we can use the two of them together: verification, explanation, prediction, and then exploration of all these kinds of material properties very generally. So when I first came into using theory with my experiments was in one particular problem, and that was looking at potassium radioactivity in the Earth, in the deep Earth. And I had run some experiments, some diamond cell experiments, looking in particular. This particular example was looking at how potassium might go into the Earth's core. And I ran all these experiments, and it wasn't what I had expected, but the results were such that I found that when I put iron and potassium together at high pressures and high temperatures, that I found an inflation of the unit cell volume for iron. And it only happened at relatively high pressures, well, pressures just into the lower mantle, and only upon melting the iron. And so we published this, but it wasn't exactly fulfilling. I didn't, what was the reasoning? I mean, I can do all sorts of hand waving on, what was going on. And what we suggested was that we were forming a solid solution, okay? An alloy. So then I contacted a colleague of mine, Gerd Steinle-Neumann, and say, okay, well, let's actually set this up, and let's look at what would happen to the unit cell volume of iron if we were to replace an iron atom for potassium. And we can do that at a number of various concentrations and so forth. And what we found was, indeed, pressure certainly stabilized the alloy in this reaction, just putting the 2 pure metals together. And also, it provided an explanation on how the potassium was actually incorporated into the iron unit cell. And that was via substitution rather than interstitial placement of your potassium atoms. So in this case, in this very easy, basic case of using density functional theory, we found that we could provide, an explanation of the experiments, as well as verification of the experiment, in that, okay, this seemed like a reasonable set of a reasonable way to I'm at a loss for words now, to explain what the data was showing us. Very simple, very easy way to use computations. Now, to run these, we in terms of kind of the highlights that Renata wanted me to put in here. What sort of computational needs did this take? Well, we had a few rather large supercells, and 6 years ago when these were run, or 7 years ago when these were run, depending on the supercell size, they may take a few days in order to run a particular volume and so forth. So it took some time, but nothing too crazy. We used VASP, and these were done on a local cluster at the Bayreuth-Geo Institute. Now we could take that a step further, and we decided to also look at how potassium would partition within the lower mantle, and then between the lower mantle and the core. Okay, so I just have here briefly the thermodynamics of the reaction, or the reaction that we're looking at. So looking at where potassium would go between perovskite and post-perovskite, or where potassium would go if you put perovskite versus the iron, and that would be the core. And again, we had to use some large supercells in order to look at potassium at relatively low concentrations. Here we have potassium would have been one of 160 atoms in the supercell. Still a very large amount of potassium, but given our computational facilities, that was about as large as we could get and still have the appropriate memory and time in order to run these calculations. Again, these were a few years ago. They wouldn't take nearly as long. But with the energies that we can calculate, the differences in the energies between these various reactions, we could then compute partition coefficients, so forth. So we take this a step further, and I'm really just sort of giving you very brief highlights on the ways that we were using these calculations. So taking it a step further in terms of potassium, and potassium being important for the Earth because of potassium-40 and its radioactive, its long-lived radioactivity, so the heating that it provides for the Earth. We also decided to explore something that had been explored many years prior to this, and that was the pressure dependency on electron capture radioactivity, of which potassium-40 decays partially by electron capture. And so actually the initial idea for this came back, was first proposed back in the 40s, and then was again looked at by Mark Bukowinsky in the 70s, and then again now. And there have been a few experiments that have shown that you can actually influence the decay constant for electron capture isotopes, in particular for beryllium-7. So beryllium-7 has a very short half-life, something of about 50 days. And so you can easily measure this decay constant, or this decay rate, in the lab. Now, that's great, and actually, here we have in the colored dots here are 3 different experiments at pressure looking at the decay rate of beryllium, and as the pressure is increased along this horizontal axis, the difference in the decay constant also increases. So the higher the pressure that we go, the more the larger the perturbation in the decay constant is actually measured. Now this is, like as I mentioned, that for beryllium-7, this can be measured in the lab, and there's certainly some disagreement between the measurements, but these were done on different samples that had beryllium-7 in. So they were, you had a beryllium hydroxide, you had a beryllium chloride, you had a beryllium oxide. So there were different chemistries. And as I didn't mention, but I have here on the slide, this decay constant is not just dependent on pressure, which is what we can measure directly in the lab, but it's also dependent on temperature and chemistry. And this is because the electron density around the nucleus, which is what is going to dictate how your unstable nucleus is going to decay. That is, it's going to capture one of its innermost electrons. If those electrons are closer to the nucleus, it makes it that much more easier to capture one of them. So we can do that with pressure. That's just pushing everything closer very easily. Or we could do that with chemistry, okay? Because of the overlap in the electron orbitals between the different elements, so forth. So we did some predictions, and those are shown here as the black curves, and the differences in the black curves are just different chemistries. And you'll notice that there's actually quite a large offset between what the calculations predict and what the experiments say that they have. So one could take these results and say, okay, well, either there's something wrong with the experiments or maybe there's something wrong with the calculations. For these particular calculations, we hope that we did a good job in that we were looking at all the electrons. We're using Wien2k in this case, and doing all electron calculation so that we can determine just how many, what your electron density is at the nucleus. Well, I'd like to say that this is actually a pretty good result in the sense that it's at least in the right direction. Because this is not always the case. We actually we actually looked at aluminum in trying to see what aluminum-26, how the decay constant for aluminum-26 would change with pressure and chemistry. And of course, we looked at potassium-40, because potassium-40, as from the previous few slides, has been my element of choice as of late. And actually, with aluminum-26, depending on the particular chemistry that you put it in, say as an oxide rather than a metal, you actually have a different result in the sense that your change in decay constant actually goes negative at pressure rather than positive. Okay? So this gave us some confidence that maybe we could use this method in order to predict how a very long-lived radioisotope would behave. That is potassium-40, which has a more than billion-year half-life. Okay? Not exactly something that's easily measurable in the lab. Okay? So I just want to highlight another reason why we might want to use computations where we can't use experiments, and that is to explore other conditions that are not readily available in the lab. And that is, we're not able to wait a billion years to test this particular hypothesis, but perhaps we can use the computations, provided we believe them, as a way to predict what's going on. So the calculations themselves, depending, of course, they get longer as you add more electrons, since we're doing all electron calculations. So the beryllium calculations are very short, whereas if you start going into the potassium and the aluminum, they take much longer times. But again, not at all very long in terms of computing power. More recently, we've been looking at other materials that are not necessarily directly related to earth science, but some transition metal dioxides, as well as looking at various forms of carbon at high pressures and high temperatures. And so in this case, we've also run the experiments, and we can use the calculations, one, to sort of complement, verify our experimental measurements, and then be able to then go beyond that, right? So for instance, we can calculate the elastic constants rather easily for these kinds of materials rather than running the experiments, which are more difficult to perform. Not impossible, of course, but more difficult. And so here again, we can predict material properties of these various. TiO2, ZrO2, HFO2,